This lecture is on the risk and return of portfolios. I'm your professor, Dr. Stephen Haggard. First of all, let's cover some vocabulary. Expected return is the return we expect a stock to earn over the next period. Could be 1 day, 1 week, 1 month, 1 year. We could also think of it as a forecasted return. Now, what we know about forecasts is that they're wrong. So this is just our very best guess of what return is going to be. Then we have return variance and standard deviation. These are statistical measures of dispersion for return. And the more dispersed the return is, the riskier it is. So these are measures of an individual stock return volatility or riskiness. Please remember from statistics that standard deviation is the square root of variance. And finally, we have covariance and correlation. These are measures of how the return of two different securities are related to each other. For instance, if one went up while the other went down, we would say that they have a negative covariance or correlation. We'll show you how to calculate these later in the lecture. We're going to work an example to teach you how to calculate expected return and variance of those returns. We have two stocks here. The first is called SuperTech and the second is called Slowpoke. And both of these stocks exist within the same economy. And that economy experiences 4 different states: depression, recession, normal, and boom. And those states of the economy occur with the following probabilities: 10%, 20%, 50%, and 20%. Notice these are stated here as decimals. In each of those states of the economy, the stocks have different rates of return that they are expected to provide. For instance, for SuperTech, in depression, is expected to return minus 30%, once again expressed as a decimal. In recession, it's expected to return minus 10%. In normal times, it's expected to return positive 20%, and in boom times, positive 50%. Down below, we see Slowpoke is expected to have no return in depression, 5% in recession, 20% in normal times, and minus 5% in boom times. Now you might ask why a stock would have a negative return during boom times. If the firm produces what's known as an inferior good, the demand for that good would be lowest in the best state of the economy. For example, think about bargain brand beer. When times are really good, do people buy bargain brand beer? No, they would typically buy something nicer, like an import or maybe Samuel Adams. And so you can think of this product as something that people would buy less of when times were good, leading to negative returns during boom time. The next step in this situation is to figure the expected return for both stocks. How do we do that? We do that by multiplying the probability for the state of the economy times the rate of return for the stock in that state of the economy. For instance, for SuperTech, we would multiply 0.10 times minus 0.30. We would then also multiply 0.20 times minus 0.10, multiply 0.50 times 0.20, and 0.20 times 0.50 to get 4 products. A product is what's results from multiplying two numbers together. Okay, now we're going to add those 4 products together, and when we do that, we get the expected return. Pause the slide at this point and see if you can come up with an expected return of 0.15 for SuperTech. We can also do the same thing for Slowpoke. We could multiply 0.10 times 0, 0.20 times 0.05, 0.5 times 0.20, and 0.2 times minus 0.05. And we can add those 4 products together and we'd come up with an expected return for slowpoke of 0.10. Pause the audio now and try this for yourself. Okay, now that we have expected returns for both SuperTech and slowpoke, we can figure out the deviation from the mean, or expected return, for each state of the economy for each stock. We do this by taking the return in that state of the economy minus the expected return. For example, for SuperTech in depression, return sub A is minus 0.30, and we're going to subtract 0.15, the expected return from that. The result, minus 0.45. Similarly, we're going to take minus 0.10 minus 0.15, the expected return, and get a deviation of minus 0.25. For normal economy, for SuperTech, we are going to take 0.20 minus 0.15 to get 0.05. And for Boom, we're going to take 0.50 minus 0.15 and get 0.35. The four numbers we've just calculated are called the deviation from the expected return. Moving on, the squared value of the deviations is merely squaring the deviation from the expected return. So when we square minus 0.45, we get 0.2025. What happened to the minus sign? Well, when you square things, the minuses go away. In fact, that's the purpose of squaring the deviations here, is to get rid of the directionality of the deviation and leave something that's only related to the magnitude. We do the same thing with minus 0.25 and come up with 0.0625. If we square 0.05, we get 0.0025, and if we square 0.35, we get 0.1225. Those are the squared values of deviation, also known as the sum of the squared deviations, or SSD. Now there's just one step left to figure variance. What we're going to do is take the probability of the state of the economy, multiply it by the squared value of the deviation for that state of the economy to come up with a product. For instance, in depression, 0.10 times 0.2025 gives us 0.02025. In recession, 0.20 times 0.0625 gives us 0.0125. In normal times, 0.5 times 0.0025 gives us 0.00125. And in boom times, 0.2 times 0.1225 is equal to 0.0245. Now what do we do with all that? We're going to add those four products together to come up with something called variance. Now variance, in this case, when we add all that together, is 0.0585. Variance isn't very useful for us because variance is in terms of percentage squared. Notice that our deviation from expected returns is basically in percentages. So when we square that, we come up with percentage square. We're adding a bunch of percentage squares together, so we're still in percentage square. How can we come up with a more meaningful number? Let's just take the square root of that, and that will tell you what the standard deviation of returns for SuperTech is. Also, we can do similar for slowpoke. So what I'd like for you to do is to pause this presentation and make sure that you can reach these numbers of variance for both SuperTech and slowpoke. Okay, so we've been able to figure out the expected return and the risk or volatility as measured by variance or standard deviation for individual stocks. But we'll soon see that it's how stocks move relative to each other that matters when we get them into portfolios. And so now we're going to move on to some measures of stock return relatedness. These are called covariance and correlation. And much like we figured variance in order to get standard deviation, we're going to calculate covariance in order to get to correlation. Now notice we've got the same states of the economy as previously with the same probabilities. And we've also got the same deviations from expected returns as in the previous slide. But this time, both stocks are sitting side by side in the table instead of one table dedicated to each stock. And the reason we're going to do that is because we're going to multiply those deviations together. And so taking column 3 times column 4 gives us column 5, which is the product of the deviations. Now, why is that important? Well, if both stocks are moving in a positive direction, when you multiply them together, you get a positive product of deviations. If both stocks are negative, then when you multiply them together, you get a positive. And so a positive product of deviations means that the stocks are headed in the same direction. And therefore, if we get a negative product of deviations, as we do during boom times, then we know that the stocks are headed in opposite directions. Now, similar to when we figured variance earlier, what we're going to do is take the probability of each state of the economy and multiply it by the product of deviations in that state of the economy. For example, in depression, 0.10 times 0.045 gives us 0.0045. Similarly, 0.2 times 0.0125 gives us 0.00250, as does 0.5 times 0.005. Finally, 0.2 times minus 0.0525 gives us minus 0.0105. We're going to take all those products that we just calculated and add them together. And the sum of all those products is the covariance. Now, covariance is a lot like variance in that it has units of percent squared. And therefore, it's not an ideal measure for us because it's really hard to interpret. And so in order to make covariance into something that we understand better, we're going to divide covariance by the products of the standard deviations of slowpoke and supertech. Now notice here at the bottom we have the formula for correlation. I'm using A to represent supertech and B to represent slowpoke. How do we get the standard deviation of supertech and slowpoke? We just take the square root of the variance from the previous slides. Okay, now let's actually go through the calculation for correlation. Our covariance was negative 0.001 from the previous slide. And from 2 slides ago, we know that the variance of supertech is 0.0585 and that the variance for slowpoke is 0.011. And so we're going to take the square root of both of those numbers, then multiply them together. The little caret symbol means exponential, and the 0.5 means 1/2 power. Taking the square root of something is the same as taking it to the 1/2 power. And when we do all this math out, what we get is the correlation of supertech with slowpoke is minus 0.03942083. Now, I've used a lot of decimal places here, but when we're doing calculations like this, you really want to keep all your decimal places right up until the end. In fact, if you're going to use this number in a later calculation, what you'll want to do is actually leave it in your calculator, perhaps by storing it in the memory. So why do we go to all the trouble to calculate correlation? Well, it's because correlation is a superior measure of relatedness, and here's why. Covariance, as we've said before, has the same units as variance, basically percent squared, so it's very hard to interpret. Correlation, on the other hand, is unitless because it's covariance, which is percent squared, divided by standard deviation multiplied by standard deviation, which is percent squared, and that stuff cancels out. Now, as a result, the correlation is much easier to interpret. Also, one other thing, correlation ranges from -1 to +1. If correlation is -1, then the stock returns are perfectly correlated. That means not necessarily that if one stock's up 1%, the other one will be up 1%. What it means is that if one stock is up, the other one will be up by a constant amount. In other words, if one stock is up 1% and the correlation is 1, the other one might be up 2%. And if the first stock were up 2%, then the second stock would be up 4%. And so the constant factor here would be 2. One would move twice as much as the other, but they're still moving in the same direction and always by this constant factor. On the other hand, if the correlations were negative, if the correlation is -1, then we'd say they're perfectly negatively correlated. And they would be related to each other by a constant negative factor. For example, one stock might be up 1%, the other one would be down -2. The first stock would be up 2% and the second would be down -4. This time the constant factor would be -2. So, why is that important? Well, we know that correlation is bound between -1 and 1, and that helps us to be able to interpret numbers. For instance, our number of minus 0.039. Is that closer to -1, 0, or 1? Well, it's actually much closer to 0 than it is to either end of the spectrum. And so this stock is actually, these two stocks are actually fairly unrelated to each other. Think about it this way. This thing is only 4% of the way toward perfect negative correlation. It's barely just to the left of 0. And so these stocks really, the movement of one doesn't have much to do with the movement of the other. Here we have some examples of correlation. If we've got perfect positive correlation, upper left-hand corner, you can see that the two stocks move together. Once again, they don't have to move exactly together as long as they're related by a constant positive number. In other words, you can multiply the small one by a positive number to get the second one, then they will be perfectly positively correlated. On the other hand, if they're perfectly negatively correlated, that constant factor would be negative. And so if one was up 1%, the other might be down 3%. If the first one were up 2%, the other one would be down 6%, and so on. Then we have zero correlation, where the movements of the stocks are unrelated. The movement of one has nothing to do with the movement of the other. Let's talk now about how to get the expected return for a portfolio. It turns out that the expected return for a portfolio is merely the weighted average of the returns, the expected returns of the components. Let's do a little example here. Consider a $100 portfolio with $60 worth of SuperTech and $40 worth of Slowpoke. The expected return on this portfolio is simply going to be the weighted average. Now, what do we mean by a weighted average? Well, first of all, we have to figure out what the portfolio weights are. For SuperTech, that's going to be $60 divided by $100, or 0.6. And for Slowpoke, it's going to be $40 divided by $100, or 0.4. Notice that Slowpoke and SuperTech have to add together to the total portfolio value because they're the only things that we have in the portfolio. Moving forward, let's get the expected return for the portfolio. We merely multiply that portfolio weight for SuperTech times its expected return. And we do the same thing for Slowpoke. We take its portfolio weight, multiply by its expected return. Now to finish up our example. The weight on SuperTech is 0.6 and its expected return is 15%. The weight on Slowpoke is 0.4 and its expected return is 10%. So we do the math and we come out with an expected return for the portfolio of 13%. Now just a reminder, where did we get the expected return of SuperTech and the expected return of Slowpoke? That came from our earlier calculations using the probability of states of the economy and the expected returns in each of those states. Now, in the real world, do we have such numbers? Probably not, and so typically what we would use is a historical average return for a firm. If the firm's business and its place in the economy have not changed dramatically over time. So we've calculated the expected return on a portfolio, and now we need to take a look at the risk on a portfolio. And of course, we always start out by calculating the variance, which will later turn into standard deviation. For a two-asset portfolio, which is what we're looking at, the variance is given by this formula. The variance of the portfolio is equal to the weight of A squared in the portfolio. So that's the same XA we looked at when we were doing expected return, only this time we're squaring it. And we're going to multiply that by, and that symbol there is sigma. That's a Greek letter. And sigma squared is a way of representing variance. And so sigma squared sub A is actually the variance of supertech. X sub B means the same thing as in the last slide. We have the weight of slowpoke in the portfolio, and we're going to square that and multiply it by the variance of slowpoke. And then we're going to add another term here. 2 times the weight of supertech times the weight of slowpoke times that thing on the end is the covariance of supertech with slowpoke. Now, don't be confused because there's no squared on that. It still has the same units as variance. So sigma A comma B is the covariance of A with B, and it has the same units as variance. And so we're going to plug all these numbers in. We've got them from previously. XA is 0.6, the variance of A is 0.0585, XB is 0.4, and the variance of B is 0.011. And then we've got all those things, the weights repeated there with multiplied by 2, and we're going to multiply by the covariance of supertech with slowpoke, which we calculated to be minus 0.001. And if you do all that math out, you'll see that the variance is 0.02234. Now, how should you do this in your calculator? Well, if I were you, I would calculate each of the 3 chunks separately and store it. For instance, 0.6, hit your squared button, multiply by 0.0585, and hit store 1. Store is STO on your calculator. And then I would say 0.4 squared times 0.011 equals, and hit store 2. And then finally I would say 2 times 0.6 times 0.4 times 0.001 plus minus equals, and store 3. Then you can just recall 1 plus recall 2 plus recall 3 to get the variance. Now remember, variance isn't of much use to us by itself. We need to find out what the standard deviation is. So we're going to take the square root of that, and we'll get 14.95%. That's going to come out of your calculator as 0.1495. But we know this has the same units as return, so we can express it in the same way, as a percentage. A common mistake that students make is to think that the portfolio standard deviation is just a weighted average of the standard deviations of the component assets' returns. And if we did the math here, what we would come up with is that the standard deviation for the portfolio in this way is 18.71%. Is that correct? No, we just calculated the standard deviation of the portfolio return to be 14.95%. So the big question is, why is the standard deviation on the portfolio lower than the weighted average standard deviation of the portfolio components? The answer is the most amazing finding in all of finance, and that is that you can have a portfolio that gives you a weighted average of returns, but through the magic of diversification, you don't have to put up with all that risk. Because it turns out that adding any asset with less than perfect correlation with a portfolio to that portfolio eliminates some risk without eliminating return. How? We're going to rewrite the equation for portfolio variance to demonstrate. Here we go. Do you see the formula that we've used previously when we calculated the variance for the portfolio? What we're going to do is take our formula for correlation. By the way, correlation can also be represented by the Greek letter rho, which kind of looks like a P. And so rho, A comma B, simply means correlation of A with B. And it's equal to the covariance of A with B divided by sigma sub A is the standard deviation of A, and sigma sub B is the standard deviation of B. So this is the same formula that we used to calculate correlation earlier. And all I'm going to do is algebraically rearrange that thing by multiplying both sides by the standard deviation of A and the standard deviation of B. Now don't freak out, I swapped sides of the equation there. That's all I did. Multiply both sides by standard deviation of A, standard deviation of B, and swap sides. Now, I can use the substitution principle and substitute this new formula for the correlation, the covariance of A with B. I'm going to plug that into that equation at the top. And once we substitute it back in, we get this equation that's down at the bottom. Now, what if the stocks were correlated perfectly? In other words, their correlation was 1. Well, let's plug that into our formula and find out what would happen. So you recognize all this from earlier, and if you still have it in your calculator, where xa squared times the variance of A is stored as 1 and xb squared times the variance of B is stored as 2, you don't have to redo that part. And so all you have to do here is take 2 times 0.6 times 0.4 times 1 times 0.242 times 0.105, and you'll end up with the variance for the portfolio if the assets are perfectly correlated. And it turns out that when you take the square root of that variance, the standard deviation of the portfolio is 18.71%. Does that number look familiar? It should, because it's the same thing that we got when we took the weighted average of the standard deviations of the portfolio components. And so, if the assets are perfectly correlated, the portfolio risk is just the weighted average of the component risks. However, if correlation is anything less than perfect, risk is reduced. We call this the diversification benefit or diversification effect. Now, here's a question. Do the assets have to be negatively correlated to gain diversification benefits? No, once again, they just have to be less than perfectly positively correlated. They could be correlated 0.99999 and you could still gain a small amount of diversification benefit. Now let's look at a real-world example of how diversification works. We have a list here of different investments and the standard deviation of their returns. And the one at the top is the S&P 500 index. You can think of the S&P 500 as being a portfolio of 500 different stocks. And below that, we have companies that are part of the S&P 500. What I want you to notice from this is that the standard deviation of the S&P 500 is lower than any one of the single components that's listed below. The reason for this is the magic of diversification. These stocks are not perfectly positively correlated, so we're able to get rid of some risk by holding them in a portfolio. Is it always the case that every single stock in a portfolio will have a higher standard deviation than the portfolio itself? No, it doesn't have to be that way. And in fact, I bet we could find some stocks in the S&P 500 that have a lower standard deviation than the index itself. But it's entirely possible to have a portfolio with a lower standard deviation of returns than every single individual component of that portfolio. By the way, that's a test question that finance professors love to ask. Is it possible to have a portfolio with a standard deviation of returns lower than every single item in the portfolio? The answer is yes.